Today we're going to be looking at some more Calculus 2 practice problems, specifically integration with inverse trig. So at the end of Calculus 1, you probably should have learned that taking the derivatives of these three inverse trig functions would give you these functions. So naturally, if you have these functions, you can integrate them to get those inverse trigs. So you will need to know these three general integrals, and then the harder part will be matching up like your u substitutions. So let's look at some examples of finding the indefinite integral. So this one, we want it to get into the form to be one of these three, right? So what I see is a constant, and it's more specifically a constant squared, right? 9 is just 3 squared, and I see an x squared and a dx. So I'm just going to match it up to this top one right here, arcsin. So if we call a equal to 3 and u equal to x and du equal to dx, then that means that we have the integral of du over the square root of a squared minus u squared, which turns into arcsine u over a plus c. So the integral is just going to turn into arcsine of u over a, x over 3, plus c. And that is the final answer. Because if you were to take the derivative of arcsine of x over 3, you'd get this function. Okay, so how about this one? What I immediately see is this on the outside, which tells me that it might be a good arcsecant candidate. So we're going to try and match it up to this form right here, right? So let's see. If we call u equal to, well, we want u squared to be 4x squared, right? Which means u is the square root of that, 2x, okay? And du is 2dx, so I should have a dx here. And finally, it looks like a can just be 1, because a squared is 1, that means a is 1 from this one. So we want a 2 and a dx inside, but we only have the dx, so we want the 2 there as well. It's not a 12. And then we're going to account for that with a 1/2 out front. We could just take that 2 out, and they would cancel, so we did not change the value of the integral. You can rewrite this as 1/2 the integral. Now we have du over, well, let's see, we also want this 2 to bring inside there. That way we have that 2x that we could call u. And then we have the square root of u squared minus a squared. And that just turns into 1/2 1 over a arcsecant of the absolute value of u over a. We're able to put an absolute value sign there because of cosine being an even function. It just doubles the domain of our answer, basically. But let's see. 1/2 times 1 over a was 1, arcsecant, absolute value of 2x over 1. It's just going to turn into, or actually we don't have this 1/2 anymore because we brought that 2 in, right? So it just turns into arcsecant, the absolute value of 2x, plus c, of course. And that is the final answer. Okay, finally, this one is going to turn to arctangent because we have some function squared added to a constant squared. And hopefully we can get this to be the du, because if it doesn't match up exactly as the du, we're going to have to look at a much harder version of integration called Trig sub, which we'll get to in a few videos. But let's see. For arctangent, it says that du over a squared plus u squared turns into 1 over a arctan u over a plus c, right? So let's try and make it match that form. We want u squared to equal t to the 4. That just means that u is t squared, which means that du is 2t. And we want a squared to be 25. That just means a is 5. So now, let's see. Because our du is 2t, we want a 2 there, So we'll bring a 1/2 up front. Now we have 1/2 times the integral of du over u squared plus a squared. We know that integral turns into 1 over a arctan u over a plus c. So 1/2, a was 5, arctan u was t squared, and a was 5 plus c. So finally, we get 1/10 arctan t squared over 5 plus c. That is the final answer. So to recap, all of these answers are different. This one is missing the 1 over a out front. And this one has an absolute value sign, and this one's like the only normal one, right? So let's look at now some harder examples. So what I see is that if we split this right here, right, this is going to be an easy u substitution, and then this one will become the arctangent. We're going to strategically split it into two integrals. It's going to become the integral of x dx over x squared plus 1 minus 3 integrals, if you factor out the 3, of x squared plus 1. So this one is going to become the inverse tangent one, right? Let's focus on the left one. This is some review, but if we call u equal to the denominator, then du is 2x dx. And we already have the x dx, we just need that 2, so we'll bring a 1/2 out front. Now we have 1/2 integral of du over u. We remember what that integrates to. And then minus 3 integrals, or we could just do the integral, because that will become exactly, well, let's see, a is equal to 1, and u is equal to x, and du is equal to dx. So this just immediately turns into arctan of x, because the 1 over a out front and the 1 over a in the argument are just 1s, so we don't see them. Then we do have that plus c. Finally, the integral of du over u is just ln of u, so 1/2 ln of u. Let's plug back in u. U was x squared plus 1 minus 3 arctan of x plus c. So that is our final answer. Now we're going to look at this one. And this one's a bit tricky, because we're going to do the same thing as splitting that integral, but the u substitution one is going to be a bit harder. So we're going to rewrite this as the integral of x dx over the square root of 9 minus x minus 3 squared plus 5 integrals of dx over the square root of 9 minus x minus 3 squared. So this one is going to turn into an arcsin, because we have a square root of a squared minus u squared. As long as we call this our u, it should work out. But this one on the left is going to be a bit tricky. What should we make u? Well, u is always the inside composite function, right? So we want u to equal 9 minus x minus 3 squared, right? Which means our du is going to turn into negative 2 x minus 3 dx, right? So we need a negative 2 x minus 3 on top. So how are we going to get that? Well, here's where the tricky part could come in. We could just put that negative 3 there, as long as we put a positive 3 there, right? Because x is equal to x minus 3 plus 3. We did not change the value of the equation. But we can take this 3 right here. We don't want it there, right? We can bring it over to the other side. So really, we did like an x minus 3 and then put the plus 3 over here. So this 3 right here and this 5 just become an 8 with that integral. And now we're left with exactly what we need on the left side. Besides that we need a negative 2 there. So we'll put the negative 2 there and account for it with a negative 1/2 out front. Right, so now we have negative 1/2, the integral of du over, let me write it like this, du over the square root of u, so u to the negative 1/2 du plus 8 integrals. Let's figure out what this one is. If we call u just x minus 3, then du is just dx, and it works out because then this is u squared, and then if a squared equals 9, a equals 3. Right, so now we have the integral of du over the square root of a squared minus u squared. We know this turns into arcsine from earlier. Right, so now we have negative 1/2, add 1 to the exponent, you get u to 1/2, divide by that new number, 2. Right, and then this one turns into 8 arcsine of u over a, which is x minus 3 over 3, plus c. Finally, we're just going to plug back in our function of u. Well, these 2 and this 2 cancel, so we're left with just negative u to the 1/2, and u is 9 minus x minus 3. U is 9 minus x minus 3 squared. All of that is to the 1/2 power, plus 8 arcsine of x minus 3 over 3 plus c. So this is our final answer. Now let's just look at one. This one isn't too hard, but we could do, but it is a definite integral, right? So when I look at this, I immediately see like an a squared plus a u squared on the bottom. And hopefully this will just be our du, and we can just call it an arctan. If not, we would have to do a trig sub, which we have not learned yet. But u, we want u squared to equal 4x squared. So u becomes 2x. That means du is 2. We want a squared to equal 1, so a is 1. So these 5 things will appear in every inverse trig integral. So du is 2 dx, so we want a 2 there and a 1/2 out front. And then this is u squared, this is a squared, so it becomes 1/2 integral of du over a squared plus u squared. But this is a function of u, right? It's a function of u. So that means we want our bounds here. See, these bounds right here are x bounds, because this is x, so these are x bounds. But we want to change these into u bounds. That way we don't have to plug in this function of u back in when we get that arctan of u over a. We want to just, if we change the bounds now, we won't have to plug back in u. So we'll just plug in, let's see, if u is 2x, we'll just plug in both of those bounds. Let's see, so u of 0 is equal to 0, so that one could have stayed. And u of square root of 3 over 2 is 2 times square root of 3 over 2. 2's cancel, you're left with just square root of 3. So if we call these new bounds 0 and square root of 3, we will no longer have to plug back in our function of u after the integral. Let's see. It's going to become 1/2 1 over a arctan, but a is just 1, u over a, and we can leave it as u now because we changed the bounds, so it's going to be arctan of u plus c, right? Oh, not a plus c because it is a definite integral, so we're just going to evaluate 1/2 arctan u at our new u bounds, square root of 3 and 0. You see, it's pretty much the same amount of work if we were to plug back in the function of 2x and then use our original bounds, u and square root of 3 over 2. It effectively does the same thing. But on some times, it's easier to just change the bounds. Okay, so let's see. this will turn into 1/2 arctan of square root of 3 minus arctan of 0. So you could just plug these into a calculator, but they're not too bad to solve because arctan of 3 is just saying which angle plugged into tangent would give you 3. And we know tangent is just sine over cosine, right? And we want that to equal square root of 3 over 1, right? And the trick is that if you put both of these over 2, you have a much more recognizable values, right? So where on the unit circle does sine equal square root of 3 over 2, or cosine equals 1/2? That happens right here at pi over 3, because sine has the big leg of the triangle, cosine has the little one, 1/2, and square root of 3 over 2. And they're both positive, so we're in quadrant 1. So arctan of square root of 3 is just that angle. Arctan would be an angle measure. So it would be, so arctan square root of 3 equals pi over 3. Right, and now let's look at 0. Right, let's see. Sine over cosine is tangent. We want that to equal 0 over 1, right? So where on the unit circle, I'll do it in a different color, where on the unit circle does sine equal 0 where cosine equals 1? Well, that is easy. Right here at 0. At 0 degrees, or 0 radians, sine is equal to 0 where cosine is equal to 1. So arctan of 0 is just 0. So that's easy. In other words, tangent of 0 degrees will give you 0, right? So now we have 1/2 times pi over 3 to get our final answer, pi over 6. That one's not too bad. Okay, now let's look at our final example. This one. You might say, this doesn't look like a trig sub, or a trig, inverse trig integral. Can't we just make u the entire denominator? And then the issue with that is that we don't have a du, because if we make u equal to the denominator here, our du would be 2x minus 4, and we do not have that 2x minus 4. So what we can do is something we learned in college algebra, right? Completing the square. Let's see. Isn't x squared minus 4x plus 4, doesn't that factor to x minus 2 squared? Let's check that. Let's FOIL it out. The first squared would be that, the inner would be minus 2x, and the outer would be minus 2x, and the last would be positive 4. So does that work? Yes. Right? So, but we don't have plus 4, we have plus 9. What I'm saying is that we could take this plus 9, right? Call it 4 and 5. Did we change the value of the equation at all? No, because we still have plus 4 plus 5, which is plus 9. Except we know that this turns into this. So now we can call it the integral of 1 over x minus 2 squared plus 5. We know we're going to get a positive 4 from here, and that positive 5 will end up becoming that positive 9. So we did not change the value of the equation. This is still equal. Whatever x value you plug into here, as long as you plug into there, you'll get the same thing. Right? So, but now you can see that we're in the form of arctangent. We have some function squared and some constant squared, forgetting the dx. So let's see. If u equals x minus 2, du is going to be equal to dx. A squared is 5, right? That just means that a is the square root of 5. Then this turns into a pretty easy arctan one. We have du over u squared plus a squared, which we know turns into 1 over a arctan u over a plus c. So let's see, 1 over root 5 arctan u is x minus 2 over root 5 plus c. And that would be our final answer. So that is how you do inverse trig integrals.